Uh, Thank you very much. I'm very honored to receive this award, and I'm sure Noam is honored as well. Um, so when I told my wife I'm getting this award, she said, "Oh, it sounds like the Giza pyramids." So, but I guess it's better to be like the pyramids than something else. But so I will start a little bit looking backward, talking about some ideas in the paper, and Noam will talk about that as well, but also about some more recent research in different directions. Uh, so first, I would start with classical economic markets, how economists understand them. And usually we make assumptions like goods are divisible, utility functions are concave. Actually, let's take the simplest case. There's just one good. So we want to find an efficient allocation of the good. We draw the demand curve, the supply curve, intersect them. It gives you the efficient allocation, the efficient quantity to trade. Also, you can implement this allocation by naming just a single price and letting people decide whether they want to buy or sell and how much at this price. And the fundamental welfare theorems tell you that efficient allocation can be supported in the price equilibrium. We also call it Walrasian equilibrium. And conversely, any price equilibrium will be Pareto efficient. Now, this is nice and simple. The question is, how does this extend to various complicated markets that you are interested in, computer scientists, but now lots of practical people are interested in as well. And this would be markets in which you have many different goods that might be indivisible. People's preferences might not be convex. There could be some strong complementarities. I think the first time people started taking this problem seriously is when they started designing combinatorial auctions for Spectrum, and it had lots of different licenses in different areas. Um, and for many bidders, they were complements and there were non-convexities. And how would these markets work? And kind of the usual computer science question is computational complexity, and could be a bottleneck. You can formulate the optimization problem, but you can't really solve it because it happens to be one of those NP-hard problems. And so people, I think it was Christos actually, who likes to say that if your PC cannot find an efficient allocation, then the market cannot find it either. So this is true, but it turns out the computers have gotten better and better. And actually, in many of these kind of combinatorial problems, given if you have an input of reasonable size, let's say bids of reasonable size, you can run them through some optimization algorithm. It might take maybe a week, but you can actually find an efficient allocation or something very close, or even exactly efficient. So we got interested in a different bottleneck, not the computational complexity bottleneck, but in the communication bottleneck, which is, the problem may not be the computation, but simply getting the relevant data out of the people. And this bottleneck also comes on the human side. So partly it's humans that they have to reveal information that they know privately that's relevant for computing efficient allocation. So information is people's values or preferences. So in this model, each agent knows privately his or her values or preferences, and they have to communicate something about values in order to find a good outcome, efficient outcome. So this turns out to be an old idea in economics, and I think the first time it was articulated, at least in English, was by Hayek in 1945 paper called The Use of Knowledge in Society. And so the specific wording he used, the specific circumstances of time and place, is something that each individual knows privately. And in order to find a good outcome, you have to somehow elicit this information. And it would be completely impractical to get everybody announce everything about what they like, what they don't like, what they can produce, what they don't want to produce, and so on. And now this idea was later formulated by Ilya Horowitz, more formalized, using a view of communication cost, defined as the dimension of the message space of a mechanism. So of course, Hayek's idea, if you remember, was that the prices somehow aggregate all the relevant information in the most informationally efficient way. And so that was a really strong defense of the market system. And Horowitz formalized this idea in a mathematical way. Now, it turns out in computer science, completely independently, there was this communication complexity model proposed by Yao, which it turns out to be very similar in many respects, but it, of course, uses the number of bits as the measure of communication cost. So how would this work in complex markets? How much communication is needed, and what's the role of prices? So the first question is, okay, in this some kind of complicated market, do prices still have any role to play? So the way I would formalize it, is it necessary to find the price equilibrium in order to find an efficient allocation? Now later on, so that's a question we have in paper with Noam. Later on, I had another paper where I asked kind of a similar question for other social choice problems, including maybe approximate efficiency, stability, fairness. Turns out that the answer is actually yes for a large class of social choice problems that we care about. Not for all of them, but for many. And then another question is, what's the right form of prices? So that's, of course, dependent on which social choice problem you're trying to solve. And then translating this into communication complexity, how hard is it to describe those prices? Of course, we also need to find them, but a lower bound on the cost is just this, how long does it take to actually describe those prices? So this is the non-deterministic problem. So now, for the sake of this talk, I'll just show you the simplest possible example that I could think of that illustrates these ideas. And of course, we talk about the non-deterministic problem, like verifying that you have an efficient allocation. It gives you a lower bound on the actual problem. So here you just have one item, and the question is, who should get it, Alice or Bob, two agents? And so these are the values of Alice and Bob on these two axes. And we want efficient allocation. That means above the diagonal, Bob's value is higher, and he should get it. Below, Alice's value is higher, and she should get it. On the diagonal, we don't really care. So the oracle here knows everything, knows the values, but must verify to an outsider that either Alice or Bob, whoever has a higher value, actually does have the higher value. So what Oracle can do is announce a message. It has a set of messages, announces a message. Each agent accepts or rejects the message purely based on his own value. So the way we show it in the picture, suppose Oracle announces a message, Alice has a rule which messages she accepts and which messages she doesn't. So the set of states, a set of value, and the rule depends on her value, okay? So the set of states in which Alice accepts the message will be some kind of horizontal band because acceptance is only determined by Alice's value. So Alice's acceptance is determined by Alice's value. Now Bob's acceptance is determined by Bob's value. So the set of states in which Bob accepts the message is a vertical band. Now the set of states in which both accept the message is the intersection, so it's a product set. In communication complexity, it's called a rectangle. It could be a rectangle or, in general, a product set. And so a message corresponds to a product set. So in this case, when this message is accepted by both Alice and Bob, we have verified that Bob is the efficient user of that object, because his value for sure is higher because this message is completely above the diagonal. Okay? So now what we really want is we want to have a message available in each state that does the verification. That means the messages have to cover our state space in some way. So we need a covering. Okay, now what does it have to do with prices? Okay, it turns out we're getting to prices pretty soon. So first of all, the cost of the oracle is related to the size of the message space. So if you talk about the worst case, it's just the binary log of the size of the message space is how long it takes the oracle to encode the message. So to minimize the cost, we try to use messages, rectangles that are as big as possible, maximal rectangles or minimally informative messages. Now, if you look at this one is definitely not the maximal rectangle you could squeeze in above the diagonal. We have to have it above the diagonal because we want to verify that Bob should have the object. But now let's try to put in maximal rectangles above the diagonal, so they will all look like this. So one corner will be on the diagonal, the other at the top right corner. So these are all the maximal or minimally informative messages verifying that Bob should get the object. Now it turns out that this is equivalent to announcing a price P and just asking Bob to say that he wants to buy at price P and asking Alice to say that she doesn't want to buy at price P. And that's exactly announcing a price equilibrium. This is a minimally informative way of verifying that Bob should get the object. Now, this is just one, the simplest example. It turns out this is a very general result. It could be proven for social choice problems, that there's some kind of price equilibrium that verifies that you have the right solution with minimal communication. Okay, now also from here you can see what is actually the communication cost, because if you look at different points on the diagonal, they all correspond to states of the world in which, let's call them diagonal states, in which actually you don't care who gets the object, but if you want to prove that you have the right outcome, you need to announce a price, and the prices for different diagonal points have to be different. So the number of prices is at least as big as the number of points on the diagonal. Well, in this case, it's a continuum if you have continuous values. So that's basically a full-link set argument that gives us a lower bound on how much communication is actually needed. This is just the size of the price space. Okay, now it turns out this idea easily extends to combinatorial auctions. Here, instead of one object, agents have values for different sets of objects. So there's a set of, there are capital M, a set is a set of objects. Little m is how many objects are in the set. The value to the empty set is normalized to 0. So here we can construct diagonal states. These are the value combinations for the two agents. So of course, a value here is the function from a subset of objects into real numbers. So in the diagonal state is a state in which any allocation between the two of objects between the two agents is efficient. It generates exactly the same surplus. So the value of Bob is the mirror image of the value of Alice, so that whichever allocation you propose, it will generate exactly the same surplus. Now, why is this an interesting full-link set? Well, because to verify that you have an efficient allocation, you need to use price, and the unique price that works in the diagonal state is a price basically equal to the value of the agent. So each agent has to receive a combinatorial price that equals to his value. So that means the communication cost is at least as high as the size of this price space. So if you have continuous values, then it has to be 2 to the power m minus 1 real numbers. If you have discrete values, it has to be this number of bits. So if you have values measured in bits. Okay, so now we get to the main theorem, and now Noam takes over.
So at this point, actually, Ilya has proven the main theorem of our paper, which basically is that any way you try to set up an auction, a protocol mechanism with a centralized auctioneer, without a centralized auctioneer, between a bunch of people, even two different players, to try to find an optimal allocation between them in a combinatorial auction, that will take you exponentially much communication. And it turns out that this is also happens to be correct for randomized communication, if you try to think about randomized protocols, which implies that even there are some distributions where this is hard on the average. So you get all of these things, and in fact, at least the deterministic and co-deterministic and the non-deterministic bounds were already proven to you, but I want to give you another proof, the way we will do it in computer science, which would also give you the randomized lower bound, and that would be the usual way we prove lower bound in communication complexity, which is reductions. So the granddaddy of the problems probably to do a reduction to would be the disjointness problem. And this has been a problem that's been well considered in the literature, starting from Yao's basic paper where he defined communication complexity. And the problem is Alice and Bob each get a bit of strings, and their problem and what they're trying to do is find whether there exists a single bit where both of them have 1. A single index where both of them have 1. And it's known that that takes a linear amount of communication, linear in the length of the string. And that's true even randomized, for randomized protocol. The point is, once you know that, you can immediately also deduce from it or do a reduction to a combinatorial auction problem. So the way we do a reduction is, given the x and y, the x for Alice and y for Bob, each one of them constructs a valuation such that if you can solve the efficient allocation for the valuation, for these two valuations, you can solve the original problem. That would be a natural reduction. And the basic idea to do that is, well, there are many different sets in a combinatorial auction. You take each one of the indices of the x and y and map them to a set. and you set the value of the valuation at that set. And there's maybe two or three small details to make this work. One of them is you need to make sure that xi and yi are mapped to sets that are complementary rather to the same set, because you want the allocation between these two sets to correspond to xi and yi. And you also need to worry just a little bit that you maintain monotonicity of the valuation and so on. But these are all very simple problems, and that would be a self-sufficient second proof for the same theorem, our main theorem. So now, once we have the theorem, we can think about various kind of other things we wish to study. So first of all, I would want to put this in contrast to the case that can be done with a small amount of communication, which is what's called a substitute, a growth substitute valuation class, where it is known that there is an efficient algorithm that uses a small amount of communication to always find an efficient allocation. And one should emphasize two things here. First of all, that it's not because this is a small set of valuations. So I didn't describe what this set is, but it is of interest. It's a large set in the sense that you need exponentially many bits to describe a valuation in this set. And yet you could you can find the optimal allocation without much communication. So something is simpler in the algorithmic communication sense in this subset of valuations than in the general class. The second point that I wish to make is that communication complexity is really a very generic thing. We allow the parties to basically send any information that they wish to each other or to the auctioneer. Really, when you try to do upper bounds, for example, the statement here that if you have a substitute valuation, you can have a small amount of communication, you usually want to try to limit yourself to more reasonable kinds of communication. And indeed, it is true that it's enough here to do what's called demand queries. So you can have a very reasonable, even from an economic point of view, protocol, and not just the generic, which is more interesting for upper bounds. So now, once you know that you can do something, we start doing our usual computer science kind of questions. For example, can you do approximation? How well can you approximate it if you can't compute it exactly? Suppose you do want to limit yourself to a small amount of communication. What can you do? And that can be figured out. You can basically do the minimum of the number of agents and square root of the number of items, and that's an upper and a lower bound. So we know exactly how these approximations. We can talk about special cases. So for example, you can talk about various different kind of subclasses of valuations, and many different subclasses have been considered in the literature. I only put two intermediate ones between the substitute class, where you can do everything with polynomial communication, exact solution, and the general case, which I just said, what is the upper bound on the kind of approximation that you can get. And these two, this is an old version of the slides. Sorry. So the TBD, there are some two numbers, lower bound and upper bound. But the point is that for various different classes of evaluations, you can try to figure out exactly what is possible and what is not possible. And I think we more or less know the general picture. We know the general picture for most valuation classes of interest, although there are some gaps. For example, the class of submodular valuation, there are lower bounds and upper bounds which are not tight. This is an old version. Okay, sorry. It's okay. Okay, so what kind of other questions do we need to ask? So the whole model of communication complexity focused just on a single issue, which is the communication costs, the preference elicitation costs that you need in order to get a good allocation. We did not worry about two issues that I do wish to talk about. The first one is incentives. Really, we are in a strategic, usually we are in some kind of strategic framework. In an auction, the different players want to have their own goals, and it's not necessary that you just participate in the auction as we describe it. The communication complexity models, the lower bounds that you have in communication complexity are even if the players are completely cooperative. Now, and on the other hand, the upper bound that I've talked about, the actual approximation that you can get, are only if the players are cooperative as we tell them to be. A really interesting question is what happens for normal strategic agents, each one of them, that is if you want to have something that's, let's say, incentive compatible. How much communication do you need to get a relatively good, approximately good solution? And but do it in an incentive compatible way. Yeah, but that and do it in incentive compatible way. So that would give you, if you wish, a harder thing to do, and you should be able to. And the question, and you should probably be able to get not as good results. And there is a long sequence of work that try to figure this out. That is, add the constraint of being incentive compatible. Now, how well can you do in polynomial communication? And I think and many papers have worked along these lines. So Ilya has some work along that line. Dubzinski has lots of work. I just saw a paper in the poster session that's going to be in the next Fox that actually reduced the approximation factor for incentive compatible allocation between submodular bidders to polylog log, and so on. There's a long list of papers that's actually going in that direction. And I would say that the basic point of view, the basic summary is like this. If we allow ourselves randomized communication, then we can do relatively good approximations. So we're not very far from the optimal without incentive constraints. We can do everything with incentive constraints. If we want to be deterministic, so we're thinking about deterministic protocols, there's a huge gap between what can be done without the problem of incentives and what can be done with the problem of incentives. And that's mostly open. And there are only very weak and few lower bounds known. The second issue that has been receiving some attention lately, and it's really interesting, our communication model allowed a long amount of interaction between the players, sort of like a market that very slowly reaches some kind of equilibrium. In reality, we would like to reach equilibrium quickly. So we have a huge amount of players, and they're all interacting with each other. And if you have n players, I don't know, 1 million different participants, you probably don't want to wait 1 million rounds of interaction of communication. And the question is, can you do this kind of, what can you do quickly in parallel? Can you also do a small amount of communication that also finishes very quickly? And again, there has been, and the most extreme case is, can you do it in one round? Everyone sends some information to a centralized authority, the government, who then is able to actually decide how to allocate everything. Does that require more communication than doing it with many rounds? And again, there have been a bunch of recent results along these lines, and mostly things are open. So we know how to do some things quickly in parallel in something like logarithmically many rounds, but not everything. And again, randomization seems to be extremely important. We don't know how to do anything deterministically. The last point that I want to make is the whole issue of communication. We were thinking about communication in combinatorial auctions mostly, in different kinds of markets. But in fact, in almost take any economic scenario that you can think of, think about the complex version of that, which is what we study in computer science usually. And communication is very often a very interesting and important bottleneck there. And it's really useful to think about what are the communication limitations of finding good outcomes, whatever you define good, in each and every scenario. So for example, one of the classic examples is the communication complexity in games. So we have a game, you have two different players, each one knows his own utility function, and now somehow some dynamic should reach, let's say, an equilibrium. That dynamic that reaches an equilibrium is sort of a communication process, what's called non-coupled dynamics. And the question is, how long will this take, which exactly translates to how much communication is needed between the two players. And there's been a significant amount of work done in that line, where the interesting contrast there is that if you just want to have a correlated equilibrium, there's a very fast protocol. Very small communication allows you to reach a correlated equilibrium. While on the other hand, if you want to reach a Nash equilibrium, that requires a lot of communication. This is like the celebrated result of Babchenko and Rubinstein. And then the same thing you can do for various other questions that you're talking about, stable matching, how much communication is needed, cake cutting, we had a talk in this conference, and many other kind of questions. So I believe that in general, take any of your problems, economic problems. We always, as computer scientists, think about the complexity cost, the computation cost of actually finding the solutions, because that captures many of the problems in reality, but also actually figure out the communication costs would be interesting. So, thank you.
Thanks. We have time for some questions, and I'll invite Ilya up as well. Yep. So to repeat, it was, how did you guys start working on this together? That's a great question.
Okay, so let us answer separately. I'll give my version. Okay, so I think each of us came at it independently, and from my point of view, it was very difficult to figure out that we both both got the same results. But we had a joint acquaintance, Ilan Kremer, who actually told me that Ilya has basically something that should be equivalent. And after many phone conversations with Ilya, we figured out that yes, they are equivalent what we have, and that we should really make an effort to try to combine them into one paper. That's my answer.
Okay, yeah, that's pretty much consistent with my recollection. But I kind of had this kind of thought about this problem for a few years, but I kind of wasn't sure how interesting it is. I didn't really know the computer science literature then. I was told that Noam is working on it, and we got in touch. Actually, I only met him after we wrote the paper, so I guess now it's not so unusual, but it's not so unusual these days, but then it was kind of interesting. I meet your co-author, yes, here. But so out of the phone conversations, one thing I remember, long conversations about whether the real world is continuous and discreteness is an approximation or the other way around. And I don't think we reached a consensus on that point, but we kind of split the difference and we did it both ways in the paper.
I'm curious if after seeing each other's proofs that you find one more intuitive or enlightening in terms of, I don't know, it's easier for me to follow this one because
I remember I was
think.
trying to check some of Noam's proofs, and it took me a long time, and then I got, why is this true? I said, okay, but you just have to write it out this way. Okay, here's an extra page, and actually it's true. But then yes, it's actually true. But I guess for him, he already knows it's true. But for me, it takes a long time to figure out.
Yes.
So I'm wondering about computational complexity versus communication complexity. We know both cloud problems, maybe they're both hard, both easy, but maybe there's a gap. So what's the difference in what these are telling us about problems?
So the question was, what's the difference between what communication complexity and did I say the right? Computational complexity and communication complexity are telling us about a problem?
Yeah, so I think that's an interesting question. And in most cases, they tell us the same story. And you believe the story more if you get the result from both different measures, both different ways to try to measure it. One of the nice things about communication complexity, you can actually prove things unconditionally. So you don't have to believe that complexity theory will not collapse in the future, which still might. And I think beyond that, there are very few cases where there is a gap. And I would say that if you find one of these cases, that's really interesting to figure out why.
Well, I have sort of slightly different understanding, but my understanding computation complexity is given an input size. So it's sort of defined for problems where the input size is not so big, while communication complexity is defined for problems, it's interesting for problems where the input size already is huge. Then if you want to have computation complexity for those, you have to come up with an oracle who is querying the inputs in some way. But then you're really counting the number of queries, which kind of boils down to communication complexity anyway. Is this correct what I said?
One way, yeah.
One way to think about it. So in a sense, it's about different kind of problems. That's kind of my understanding of it.
We have time for one last question, and maybe any last question? Okay, so I think we'll move on to the next talk. Thanks, guys. That was great. Let's thank him again.